I'm excited about today's presentation because a lot of the details we are going to go over today come from our experience in teaching builders and working on passive house projects. So I'm going to go over some details, going to go over some building science, and then I look forward to the chat and Q&A after this. I'm going to start sharing my screen. Please let me know if you can see my screen right now, correct? Awesome. Thank you so much. Yeah, our mission, we used to be architects back in 2009 when the company was founded. And when we moved the company to the US in 2017, we made our mission to bring the latest building science to mainstream construction. Today, we're going to talk about some unusual suspects in building science, something that is impactful, does make a difference, and it is often overlooked in projects that we work on. I followed this movie that I loved, The Usual Suspects. I also realized that this is a movie that is 30 years old. So it makes me feel a little bit older. I was in high school back then, but that is what we are referencing a little bit in this presentation. If you have not watched the movie, it's a great one. So who's Emu? We were architects. Emu was literally founded by Mariana Pickering and I in 2009 as an architectural practice. And over the years, we evolved to providing mostly training. That is, we saw a great opportunity for faster and more impactful change in the market by educating people more so than working on individual projects one at a time. We have developed a hands-on workshop that we take around the country. We were in Brooklyn last week. We are going to be in Boston next week. We can talk about later about upcoming dates, but it is a lot of what we do. And we do some consulting as a way to keep our curriculum relevant. We see ourselves as a teaching hospital. So actual projects are a way for us to be familiar with new products, new challenges, different climate zones, different types of projects. So it's a way that keeps our teaching alive and current. So what Emu does is actually a lot of training. About 2/3 of what we do is training, and the remaining third is consulting. The training is mostly online. We have the in-person boot camp that is probably what is most visible on social media. If you follow us on Instagram or YouTube, you see a lot of that. But that training is also available online for the course part. Consulting, we do some of that, but it's really to help alumni on the first projects and to keep the curriculum relevant, as I mentioned. Now, this is who Emu is. I would like you to try and put in the chat who you are. So it's always good for me to have an understanding about who I'm talking with, so that when we have the conversation later, it's going to be more fun and more defined. So please put in the chat if you are an architect or a designer, please type 1. If you are a builder or a contractor, please type 2 in the chat. 3, if you work in construction with some specialty, for example, if you're an engineer, if you're an HVAC installer, if you rep or install windows, things like that. Type 4, if you work in permitting, inspections, or testing. We don't get many of those, so I hope we have some in the crowd today. Or something else, but you're still a professional. And if you're not a professional working in construction, then if you're here by mistake and regretting it, then type 6. You're still in time to leave. And if you just want to improve your own house, type 7. Or if you're just interested in green building, please type 8. This is kind of helpful to get a sense of what audience we have today. And it is, please type your number as you go in. Now, why do we care about buildings? This is something that when we teach our builders and our architects, we always try to go back to the why. Because if we understand the why, then we have a good sense of how to move forward. A lot of people that come and take our training or that we help with their projects via consulting, they don't necessarily want to certify the buildings. They want to build better and use passive house science to get there, to have more resilient buildings, to have healthier and buildings with higher comfort and higher indoor air quality, as well as they may have goals to get to net zero. They may have goals to significantly reduce their energy impact on the planet. So that is why they come to us. But they really don't always come to us just to get a plaque or certification. So we spend a lot of time inside buildings. Do you know how long we spent inside our buildings? Can you please type in the chat how long, what percentage of time we spend inside buildings? Let me see the chat. This is intended to be a little bit interactive. Oh, 90%, 90%. Okay, good. A lot of you have done your study. Very good. And so there's an architect from the Netherlands that Rem Koolhaas, that had this concept of voluntary prisoners of architecture. We people, there is no law that forces us to be inside our homes. Yes, there are people in jail, but that's different. Most of us decide to be inside the building because we get shelter, we get protection, but we are voluntarily doing so. There's no requirement for us to do that. So these are some examples of buildings. This is a brewery in Colorado. That is my beer glass. And I was so uncomfortable. It was so cold that I only had one beer instead of a couple. And they literally lost business because the place was so uncomfortable. This is mold. That is the result from a partial energy retrofit. The old building did not have any mold. Then they air sealed the building, they replaced the windows, they did not do anything to mitigate thermal bridging, nor did they anything to provide continuous ventilation. And the building filled up with mold. Now, the building is more energy efficient, but it is a lot less healthy. And this is one of the risks that we face in pushing the envelope without really knowing what we're doing for the building science. This on the left-hand side kind of ties to the conversation we were having before the presentation started about monitoring CO2 and indoor air quality. This is an apartment I used to live in Colorado, a building that is less than 10 years old and has no continuous ventilation. And in the shoulder seasons in the spring, I was fighting, this is actually in the summertime, but I was basically fighting the need for fresh air and to keep my CO2 low with the intention to be comfortable. And that is was basically impossible to do because the building was not set up to have indoor air quality. So that is a building that complies with the latest energy code, but does not have a way to control indoor air quality, which is very important. So another question for you all, please type in the chat. This is something that I ask all the time. So if you've seen me present in the past, you probably know the answer to this. How long does a family stay in a house they just moved into before they move out again? I see a 6, I see a 10, 5 to 7, 4, 13, 13, 7, 7. So this is awesome. We have all numbers in the spectrum. We have 7, we have 25, we have 5. Years are just numbers, I heard once, which is fun, but it was a different context. How long have you lived in the house you live in right now? 10, 32. Okay, pretty high numbers there. So this is very important because as we make recommendations to our clients, as we make decisions to invest in a building that is built better and is more resilient, we're going to be asked about what is the return on investment of this greater investment, what is the energy savings and all of that. And if we don't have the frame of reference for the time clear, then we are giving ill advice to our clients. And the national statistics that has nothing to do with passive house, it's provided by NAHP, the National Association of Home Builders, is that in average, families stay in homes for 13 years before they move out again. And they have, this statistic is over 10 years old. So for the past 10 years, continuously, it has been 13 years. And the number is increasing, so people are staying longer. There was COVID, there is higher interest rates, it becomes a lot more expensive to build. So people spend a lot more time in buildings that we may believe in. If you believe that people stay in a house 3 to 5 years, change that, change that number in your head. So this is extremely important for building science because it provides us a context so that based on which we can advise our clients in our projects. Then this is where we start looking at the usual suspects or unusual suspects. This is a lineup photo from that movie. Again, great movie. If you've not watched it, it's excellent. It's almost 30 years old, which I did not realize until last night. So looking at how we can make a building more energy efficient, in a new house, brand new house built to the latest energy code, where are the areas of the greatest heat loss? Is it the exterior walls? Is it the ceiling or the roof? The air leakage? Is it the window exterior doors? Is it the doggy door? Or is it the slab or losses through the ground? Please type in the numbers that you believe that to be. I see air leakage, I see slab, I see a lot of air leakage, I see a lot of windows. Air leakage, excellent. And I didn't know that, so I included this in part of a study that we published last year, because we ourselves, we call Emu, we curate our own curriculum, and people were asking, and clearly this changes depending on different climate zones and different types of buildings, if it is a retrofit, if it is a commercial building and whatnot. But I had no idea. So this is part of this study that we published last year with 50 different projects, single family home, new construction, where we compared different building standards. And we found that this was the typical breakdown of the heat losses over those projects. Now, those projects were intentionally selected to be in different climate zones. They are all new construction. And if we apply the 2021 IECC energy code, then this is the breakdown that we will find in average in those projects. In other words, number one, windows and exterior doors. That does not include air leaks. Air leaks are lumped up in the air leaks in the blue here. Number two is exterior walls. Number three is heat losses through the slab or through the walls, through ground, to the outside air. And only number fourth from the top is the air leaks that count for the heat losses in these new buildings. Yeah, I see that it's very hard to read. I'm sorry about that. Maybe I can provide the PDFs after this presentation. But long story short, in average, you can expect the greatest area of heat losses in a new house to be windows. The second one, the exterior walls. And the third one to be the floor or the slab on grade, heat losses through the ground to the outside. And the air leaks is only the fourth one. So this was one of the surprises that we had as we were processing the data from these 50 different projects. Now, something that I found to be interesting is that was for the 2021 energy code. What about passive house? So we modeled, as part of this study, also for all these 50 projects, if they were to meet the PHI passive house, and this is what the breakdown would look like. So it's actually very similar breakdown. Windows are still, they're still the number one cause of heat losses. And the second one is still the exterior walls. And the third one is still the heat losses through the ground. So the difference is that in using passive house, we significantly reduce those losses. But the kind of breakdown or the hierarchy remains kind of the same. Number one, windows. Number two, walls. Number three, losses through the ground to the outside. And that's why we're going to have a couple of examples of that today. And the losses through air leakage is something that is very talked about. It's very present on social media because it's very important for the durability of the building, for buildings to be airtight. But in terms of the overall weight of the losses through air leakage on the overall, we're talking 10%. We're not talking 50%. I heard builders say that, oh, I saw on Instagram that air leaks count for 50% of the heat losses. And that may be true for old buildings that were not retrofitted, where you have a ton of air leakage. But if you start looking at buildings that have pre-ACH or air leakage or tighter, then those losses through the air leakage is just 10% or less of the total. So let's start talking about windows. This is the first in our lineup. And why do we care about windows? I mentioned that I was so uncomfortable at this bar in Colorado that I had to leave. And this is something that is extremely common, not just in breweries, but everywhere. And in fact, there is no requirement in the regular building code to provide thermal comfort. That is something that Passive House does include as part of the certification requirements, as opposed to building code and other building codes like Energy Star or the Zero Energy Ready Homes. They don't really address thermal comfort. Colorado was the first place I lived in where I had ice forming on the inside of my window. And this was during COVID. This was 2020, 2021. And I had not much to do. So I posted a picture of this on social media, including LinkedIn. And on LinkedIn, we work with a lot of window manufacturers. So I have a lot of connections on LinkedIn that are in the fenestration and window manufacturing industry. And I got so much pushbacks because I posted this picture, and to the fenestration industry, to the American window and door manufacturing industry, it is accepted and it is considered to be normal to have ice forming on the inside of the window. I did not have a humidifier. That was just a cold day outside. I had ice forming on the inside of my window, no humidifier, and that is accepted. That is the normal, that is standard for American-made windows. And that is very sad. So just to give you context of what is out there, this is another analysis from the same study going over 50 different projects, where each dot is one project and the color of the dot shows which building standard we were considering. There is a free download at the end for this study if you're interested. But basically, this graph shows that Fuse and PHI follow the thermal comfort analysis as opposed to building code having no relationship between the requirements and the thermal comfort. So just for context, we care about windows because they are cornerstones of our buildings being comfortable and being free of ice and free of mold and condensation. That is why we care about windows. Now, in a new, well-installed high-performance window, so it's a new window, it is installed well, and it is a high-performance window, where do you believe to have the greatest heat losses? This is another step where I ask you to type in the chat. Do you expect that losses to be at the head, at the jamb, at the sill, at the glass edge, at the window frame, or through air leaks? New window, well installed, high performance, where do you see the greatest losses? I see some air leaks, I see some window frame. Very good, very good. Glass edge, okay, cool. Thank you for participating. And we took one window that we work with often. This is a B-grade window made by Alpen in Colorado. We just took this one because there are things that we can simulate with the software, but there's data here that also comes from field testing, specifically the air leakage. And you see the breakdown here. The biggest blue wedge on the left-hand side is heat losses through the frame. The second one is, let me jump ahead a little bit. Number one is conduction losses through the window frame. Number two, in lighter blue color, is losses through the glass. And number three is the thermal bridge at the window to wall connection. We're going to see in a second what that is. The fourth one is the glass edge thermal bridge. And then last come the air leaks at the connection between the sash and the frame and the window to wall connection. These are the data that we got from lab testing and field testing from Alpen. Again, a lot of builders that come to our training, they know that windows are going to leak at some point, but really the air leakage is a very, very small fraction of the losses that we have through a window. It's like 1% or 2%. Majority of that, once we switch to a high performance window with triple pane, then the frame becomes extremely important. So this is what we were talking about. This is a section detail. This is the heat losses analysis. The conduction to the window frame is these blue lines, conduction to the glass. Then we have the thermal bridge connection between the window and the wall. Basically, this bypass effect that you see in the little arrows in the diagram here, this is from our thermal bridge modeling analysis software. And you can see that those heat going around the frame. Then there's the glass edge thermal bridge, which is number 4. And only number 5 and 6 are the air leaks between the sash and the frame of the window itself and at the installation of the window, assuming this is a well-installed window. So this is something that in the context of windows being the biggest cause of heat losses, then within a window, air leaks is actually very, very small, assuming it's a good window and it is installed well. That's why we train builders to do that. But it's extremely important to choose a good frame and a good glass, because otherwise you may have a very well installed, very poor window. And that will still get you uncomfortable and ice and condensation, because that is a lot of the losses are through conduction, not through air leaks. So the next one up, and we saw that in the pie chart for the heat losses, is heat losses through the ground. And this is something that blows builders' mind when we mention it, because there is a belief that the ground is at a constant temperature, so it kind of does not matter. And it is all the opposite. It does matter a lot. It is the third greatest area of heat loss in a typical new construction. So this is a couple of details showing the heat losses to the ground. This is a detail that we have for a project in Colorado where we're looking at a condition. So left-hand side is the outside. Then you see it's a intermediate floor between a conditioned basement and the main floor. Downstairs, you have the insulation inbound. Let me see. Somebody says we cannot see the new slide. Can you see the new slide now? Can you see a blank slide? Okay, cool. Thank you for that. So this is a typical construction detail where you have your losses. This is what the fun diagram shows. And you can see there's a lot of arrows that from the downstairs go through the ground up to the outside. And in this case, it's not a big deal. We have enough insulation through the floor to not cause any issues. This is a case of a double wall. And these details vary significantly in what strategy we need to implement, depending on what kind of assemblies we are trying to connect. Now, if we do the same exact detail, but with a 2x6 wall with exterior insulation, it looks like this. This is something that we created for our textbook. The one above is from an actual project. We wanted to replicate the same and show some issues with the different types of assemblies. So the one below is a 2x6 wall that has continuous insulation. And one may think, oh, my insulation goes 1 or 2 feet down into the below grade, and I may be good enough. The reality is that heat is very good at finding ways to escape, and heat moves in all 3 directions. So this is an example where we have a very big thermal bridge because there was no insulation under the wall plate. So the detail above with the double stud wall, great, no problem. The one below, it does need some work because we have a lot of thermal bridging. And this is where believing that the ground is at a constant temperature and it kind of does not matter, you don't have to insulate, may lead the project to have issues because heat is very good at finding the easiest way out. Now, to expand on that, we have one more example for the heat losses to the ground. This one is from a retrofit of a project in Montana. Detail of an existing floor that was kind of sunk into the dirt, and they have an existing slab, and they have the exterior wall. They put extra effort in having a double stud wall for the wall above grade, and they also added exterior insulation. As opposed to the slab, they were planning on not doing anything because they assumed that the ground is at a constant temperature, so it doesn't matter. But once you actually do the analysis, this is what the heat flow looks like. So blue in the analysis means not much heat flow. So the wall is a double stud wall, has exterior insulation, it's awesome, super performing. The slab has zero insulation, and so that becomes a highway for the heat to escape to the outside. And this heat flow is not just at the perimeter, it's under the entire building. So this is a section showing about 12 feet into the building. You still have heat jumping from the room into the existing slab, into the dirt, out to the exterior air. So this is, hang on, I lost my cursor for a sec. This is a very typical path for the heat to escape from the inside through the ground to the outside air. And that is what we were seeing in that pie chart that we saw at the beginning, where heat losses through the ground counted for over a third, were the third greatest cause of heat losses in new construction. Because it's not that you're losing heat to the dirt and then you're warming up Mother Earth. The heat escapes through the dirt and it goes to warm up the exterior air. So that is very important to see, and that is something that blows the mind of a lot of builders we work with. Then going forward, something that we come across all the time in projects that we work with is metal flashing through insulation. And this may sound like a conflict of interest. The reality is that we have ways to do so much better than what we have been in the past. And this type of analysis allows us to see how impactful these details are. So what we're talking about is these are two exterior walls. The left-hand side those are two identical walls, where the pink is the stud cavity, your 2x6 space with insulation. Then the orange is your sheeting, your greenish is your exterior insulation, and the L-shaped lip that we have on the left-hand side is a 20-gauge aluminum flashing that is very typical in what is called high-performance construction. That is not really high performance. So on Instagram, if you look at flashing details, you're going to see a lot of that. And that is oftentimes a problem because this is something that in a home project, you may have 300 linear feet of this detail easily. And so the impact is very large. And on the right-hand side, we modeled just leaving a gap in the insulation, 1 inch between your insulation boards. And what we found is that they actually act very similar in that you see that metal fin on the left-hand side really sucks the heat from the sheeting and dumps it to the outside. And if you look at the isotherms, they look very similar. And in fact, performance-wise, having a metal flashing element like that penetrating through your insulation has about the same thermal bridging effect as leaving 1 inch gap in your insulation. Now, you would not leave an inch gap in your insulation, so you should also look at non-metal flashing details for your project. Flashing is extremely important, but today there's so much good technology to have these details and avoid using metal to do that. So this is extremely important. These are small details, but flashing, you may have 200 or 300 linear feet of that detail in your project. So it's extremely important. And I hope you cannot unsee this because it's literally like leaving an inch gap between your insulation boards. Looking at the last one, this is, if you have seen the movie, you see that this guy on the right side is the bad guy. If you've not seen the movie, that might be a spoiler. I'm sorry. And a big quotation for the movie is, the greatest trick the devil ever pulled was convincing the world he does not exist. And I rephrase that to, the greatest trick building code ever pulled was convincing the world that prescriptive checklists do the job. And this is a greater picture view of how we approach building science. Part of the study that I mentioned earlier, we compare different building standards, but also we did little side projects. And part of that, we also compared two standards. One is performance-based, in this case was low energy building by PHI, to a prescriptive, in this case was by Fuse. We picked those because they were kind of close to each other in the energy performance that the buildings would get in implementing these standards. So we selected these two standards. We chose projects, out of the 50 projects that we covered in the report, we chose the ones that fell within 20% of each other in terms of performance. We ended up with 18 projects that met this criteria. And what we found is that so these are 18 projects that get to the same energy performance using the performance-based approach, PHI, low energy building, and the prescriptive approach, Fuse prescriptive. Now, a pushback that we get from builders is, for the performance-based, someone has to do the energy analysis, and that is perceived as an extra cost. Now, if you're trying to be more resource efficient, you want to look at how your building performs, as well as what you need for that performance to happen. For these 18 projects, we saw in average that the performance-based projects were needing 800 cubic feet less insulation to get to the same energy performance. I'm going to say that one more time. The projects that were using the performance-based approach, because they were able to tweak the passive solar gains and other parameters of the envelope, they were using 800 cubic feet in average less thermal insulation to get to the same energy performance than the project using the prescriptive approach. It's a ton of insulation. It's a truckload of insulation. If you're trying to be resource efficient, if you try to minimize the embodied carbon, if you try to be cost efficient, 800 cubic feet of insulation is a lot of money. So this was one of the results that we found. And looking at the cost analysis, we factored in what we charged those projects for those analyses. And in average, once you account for that insulation that was not used, so saved, projects using the performance-based path were saving in average $5,000, even when we accounted for what we charged. So in other words, we need, in my opinion, we need a systemic change of approach to high-performance buildings where we move away from prescriptive approaches and we start implementing a performance-based approach, whichever the goal. I'm not saying that every single project has to meet passive hours, but we want to be smart about it because there are so many factors to be brought in: embodied carbon, resiliency, comfort, condensation avoidance, all of that. And a prescriptive checklist just does not do the job. If you want to learn more, this is the QR code where you can download the study. This is the training that I mentioned. It is online and in person. We're going to be in Boston next week. And then we have the West Coast on our radar for after the summer. And if you just have questions, we have a free info session every first Thursday of the month. Thank you all for your attention, and I look forward to questions and chatting more.
Wow, thank you, Enrico. That was awesome. I agree. Probably the prescriptive measure shouldn't be, taking the front seat and the only focus when there are so many other details like you showed us today. So thank you so much. I know we have some really great questions in the chat. And before we get to those, I would like to throw it to Zach to thank our sponsors today.
Yeah, thank you, Sarah. And thank you, Enrico. That was really incredible. Really appreciate it. So I'd like to thank our sponsors that make everything we do at Passive House Accelerator possible. So starting with our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Big thank you to NYSERDA. Thank you too to our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Glavel, Minutair, Partel, Rockwell North America, Stocorp, and Zola Windows. And thanks to our champion sponsors, Bewizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050. And thanks to our patron sponsors, Brennan, Euroline Windows, Holstrom System, Innotech Windows and Doors, Lamilux, Longboard, RDH Building Science, and Sanderson Sustainable Design. Thanks, sponsors.
Thank you, sponsors. Thank you, Zach. We will now begin the Q&A. So, we'll ask the questions and you can unmute yourself to ask the question yourself, or we could do it for you. So, Sarah, can take it away.
Awesome. Andrew Peel, you are the first today to ask your question. Are you still online and would you like to ask your question yourself? Maybe a couple moments here.
Oh, sorry, this is really dark. Okay, sorry. Sorry about this alternative location today. Yeah, so the comparison of relative heat loss for the different aspects like the windows, walls, air tightness, so on. You listed both for passive and for typical new construction. Air tightness comes in at number 4. But I was wondering, is that for the conventional new construction being number 4, is that based on IECC prescriptive, like whatever they require, or is that based on actual test data? Because what we found in Ontario, the actual air tightness of conventional buildings, we don't have a lot of data, but data I've come across, it varies from like 2 ACH to 9 ACH at 50 pascals. So the relative contribution air tightness is going to vary a lot across new homes.
That is a study that was comparing building standards themselves. So it was assuming the 3 ACH 50 for the IECC prescriptive.
Okay. So in some cases, optimistic for sure.
Yes, it is. One of the outcomes of that study was that depicting the regular energy code as is, it's very generous with regards to the regular energy code, because it's oftentimes not enforced, or when it is adopted with changes that are never more restrictive. I've not seen any changes in the implementation to be more restrictive than the actual building standard. Yes. It was generous to building code, not to passive house.
Right. Okay, great. Thank you.
Yep.
Thank you, Andrew. So we'll move with Randy Van Straten. Give a couple of seconds, see if Randy's still on the call. No, maybe he jumped off. So Randy's question was, is this analysis using PHPP? Does the software overestimate the loss to the ground in a fair bit? Oh, sorry. Does the software overestimate the loss to the ground a fair bit? Regarding the air leak study slide.
So is the question if the losses to the ground are overestimated and the air leaks are underestimated? Is that the question?
That's what I think he means. Yeah, so let me reverse the question. Maybe I wasn't good at reading it. So the beginning is this analysis using PHP? Does the software overestimate the loss to the ground a fair bit? Ehrlich study slide. Yeah, I mean, I guess you would need to explain what he heard to then ask the question, I guess, on that slide.
To my knowledge, PHP implements the state-of-the-art building science with regards to the heat losses to the ground, including the ISO 13370 standard for the calculation of the heat losses to the ground. So that is my answer. I've never heard of PHP overestimating the heat losses to the ground. I know it may come as a surprise because a lot of people underestimate the heat losses to the ground.
Right.
And again, it's losses through the ground to the outside air. That is the big difference here.
Yeah, I mean, I guess it's more about when you're thinking about heat loss, what seems like common sense, it turns out to be different when you actually do the calculations, which happens often.
Well,
to me at least.
Hence the title of the presentation, The Unusual Suspects, because these are a lot of the details that we come across in teaching this and doing a lot of analysis on projects. And it is where a lot of people are kind of baffled and surprised to learn about.
All righty, Richard Gardner, you are up next. If you're still on the call, you are welcome to ask your question.
Yes, thank you. So in a cooling dominated climate, the heat loss to the ground is a beneficial thing. Any comments, feedback on taking advantage of that?
That is a very good point. Thank you. I have found that to be true, that statement to be true most of the time, but it also depending on what temperature we set the building to be at. So we have, say, Austin, Texas, or Orlando, Florida, we have some itty-bitty of heating and we have a lot of cooling, right? So if we have no insulation on the slab, we're going to have heat losses from inside the building in wintertime through the ground to the outside, what we just saw. As well as in summertime, when it is hot outside, we want to keep the cooling, the inside of the building cool. The ground and the lack of insulation between the house and the ground helps dissipate some of the heat. So you're correct in what you're saying. With the exception that that relationship for the cooling really depends on what temperature you want to run your building at in the summertime. If you want to run your building at 75, you're awesome. If you want to run your building at 68 degrees in the cooling season, you're going to have heat gains from the ground up. This is something that they found in the passive house built in Dubai in 2015. A personal friend of mine is the passive house consultant that did that project. And their request of the clients, this is an office building, was to run the building at 68 degrees year long in Dubai. So because there's a such stark delta, they ended up having a lot of heat gains from the ground up. So that relationship is true, what you're saying, but it is not always black and white because it also depends on what temperature you run your building at.
Yeah, I guess currently following the set points that DS recommends, we've also noticed that perimeter insulation is just almost mission critical. Or under slab insulation is kind of tricky in our climate zone.
Yeah, the Fuse and PHI have the same set point temperature for certification that is 77 degrees, which is, in my opinion, not really realistic for the American audience. For this study, instead, we use 74 degrees set point for cooling and 70 degrees for heating. That is different from PHI and Fuse use the same 68 for heating and 77 for cooling. And that is just that change between 77 and 74 did change that parameter for the insulation. So it is a bit tricky.
Thank you. I never considering the set points.
There's
keep
plenty
that
of
in mind.
space at the bottom of the rabbit hole.
Yeah, for sure. It's a big difference though from 68 to 70 when you're thinking of heating. I mean, to me, 68 is kind of cold, so I would try to go on the higher end.
Yep.
So the next question is from John. Is John on the call? Doesn't have a last name, unfortunately.
It looks like he signed off.
He said, oh, okay. Well, so I think his question is it's relevant, and I think you can expand a little bit on it just for more reference. So his question is, what manufacturer makes no metal flashing? And I can expand on that by asking Enrico if you can provide some guidance on which materials would be preferable than aluminum or steel flashing if you do have to, go through it because of construction.
Yes, it depends on which flashing detail we're talking about. Oftentimes, something that we have, for example, at the window sills, doing some liquid applied or tape flashing can be very good. And that has no thermal bridging. It does require some pitching of the sills, some extra strategy, but it is something that we do all the time in our projects. And then for other flashing details, there are some vinyl profiles or fiberglass, and those are basically have the same thermal conductivity as wood. So they basically, their thermal bridging exists, but it's like 1% or 0.1% of the thermal bridging that you get using aluminum or copper or steel. So that is, those are options for other types of flashing details.
We have a couple more questions, but before I jump into the next one, Enrico, I'm wondering if you wouldn't mind sharing your QR code again for some folks.
Yeah. Let me do that real quick.
Awesome.
In fact, it's still up, so.
And it's great that, we got folks that are curiously waiting for that. There we go.
Yeah.
All righty. I have one question for you, Enrico, and that is, what are best practices for reducing thermal bridging across sill/jamb/head framing?
That's a great question. In the first place, we want to see it's really detail specific and somewhat climate specific because the climate dictates the wall assembly. In life, what we saw in the presentation today is that the frame is the greatest area of heat loss in a high performance new window. So in life, we typically extend the wall insulation over the window frame to add some R value over that. And that means that the window is installed in the middle of the wall thickness. That kind of sets the stage to saying that we do not want to have a metal sill pan coming all the way under the window to the inside. That sill pan can go to the exterior face of the window, but then the actual flashing of the window can be either a outward pitched buck that can be sealed with either stretch tape or liquid applied, but that becomes the primary drainage plane for that detail. Along the same line for the head detail, if you have exterior continuous insulation, we don't typically it's all about balancing cost per reward, right? So if you have exterior insulation, we typically don't do extra insulation at the headers, because that insulation is on the exterior is enough, and typically your window is lined up under them. But this is something that will be project by project details, I know that I only partially answered the question.
Well, that's usually the answer. It depends when you're working on passive house projects. It all depends on where you are and what your building is. I mean, I can tell you from experience that wood bugs or just wood around the frame to try to help minimize that is not well received when you're working in multifamily projects in a big city. So
Yeah.
they're always scared about the rotting or problems
Yeah.
with the wood material. So
Yeah, and there can be options for fiberglass there as well, or it's always a compromise when you're designing anything. So we're talking just about thermal bridging. There's going to be priorities for air sealing, for water drainage, for aesthetics, for structural and wind load resistance. So it's always a compromise of those. What is important is don't have a big steel lintel or a steel header that is uninsulated, just those big elephants in the room for thermal bridging. The bottom line is that there is a fair amount of flexibility if you're doing the actual analysis. The analysis is a way to find that compromise.
right. So the next question would be from Jacine Rousseff.
Thank you. I was just asking whether you have similar studies or reports that point to the similar issues that the commercial construction, so we can reference those when we're trying to educate our colleagues and designers on some of our projects.
I know there is a similar study being worked on by RDH and others about multifamily projects. We are not part of that study, and I don't know if the study is already completed or if not, when it's going to be completed. I talked to someone about this last fall, so I'm not up to speed about how they're doing with the design, with the research.
That's pretty interesting. Alrighty. Up next, I have a question from Salvatore Zarella. Salvatore, are you online, and would you like to ask your question? All right, Salvatore, I see that you're online, but I will ask your question. If you would like to jump in, totally feel free to interrupt me. All right, Enrico, my question for you is, can you provide a real-life example of the prescriptive versus performance in which you used as your example to impact the material requirements that you mentioned in significant savings in insulation?
Yes. The example that I have more present in my mind is about the window package, which is even greater savings. And it's similar because the team coming in was expecting to need performance X, and instead the analysis showed performance Y, and there was a significant amount of savings. That is something that, to meet passive house or to have comfort by means of the passive house comfort analysis is really climate specific, meaning that, passive house windows, you may think, oh, it's triple pane windows, but in a big part of the country, that is not necessarily true. So something that we do oftentimes in Southern California or Texas, or we have project in Alabama in the South, we get asked what kind of window package they need to install, and they oftentimes start with a triple pane baseline, and the thermal comfort analysis shows that they actually don't need that, and that is several thousands of dollars saved because you're no longer needing a triple pane. You may get away with a double pane. Again, we're not in the business of selling triple pane windows. We are trying to get to a comfort level, and that is very climate specific. But that is, we use the analysis to see what U value or what R value the window package needs to be to meet the comfort analysis.
Sorry about that, guys. I was a little bit out of pocket when you initially asked the question. But Salvatore here. Sarah, thank you for asking. Just to pinpoint a little bit, I think that I speak maybe predominantly for many of my colleagues, is that targeting a 0.15, 0.14, U value, BTU hour foot squared Fahrenheit on a window is kind of just, a go-to. It's pretty straightforward. It's somewhat off the shelf at this point for us, and all of them are pretty much triple pane. And I guess, working in a much warmer climate makes sense to drop off that other layer of glass. More specifically, thank you for answering the question related to windows. Do you find that in other areas, prescriptive versus when you're talking about 800 cubic feet, were you seeing that impact related to change in performance on window specifically? Was that when the example had come up?
So that 800 cubic feet, in the first place, which climate zone are you in?
Well, I'm in a cold climate. Climate zone 5, specifically myself.
Okay, so kind of middle of the road.
Yeah.
We found that just getting the right passive solar gain coefficient, so the right coating on the glass, makes a much bigger impact on the performance of the building, on the year-round performance of the building, so summertime and as well as wintertime, compared to the 23rd or 24th inch of insulation. And if you're using a prescriptive path, then you have no way to assess that change in just changing the coating on the glass. You just don't know. And so there is a tendency in the market to default to low gains glass out of not knowing, and that is what everybody's doing. But in climate zone 4 and higher, in residential construction, it is typically better for the year-round performance to have high gains glass. And without an energy analysis, you just don't know what's happening to your building.
Higher solar gain, you're talking about?
Correct.
SHGC values that are greater.
Correct, yes.
So would you take a stab at it? Some 0.55, 0.6, 0.62, is that what you're...
Well, for true triple pane, we typically are around 0.5, 0.52 with 2 low E coatings, typically. And even
on the south side.
Very good question. Typically on all sides. That is a very good question, because there may be a belief that, and clearly this is also project specific. There is a belief that you always want to have your west facing glass with low gains glass, which adds a layer of complexity to the order, to the installer, to everybody, to the specifier. But really, when you look at the actual numbers, high gains glass in residential construction on all aspects of the building is oftentimes the best case for the year-round performance, including cooling. So you're gonna have a little bit of more cooling, but you have so much less heating. Also, because if we're talking heat pumps are a lot more efficient in producing cooling than they are in producing heating. So once you factor that in, you want high gains glass. Clearly, if your building is a wall of glass facing west, that is a different story. But a regular design, we see that, especially in climate zone 5 and higher, so colder, we typically spec high gains glass. And high gains being 0.5 solar heat gain coefficient.
So just to be clear, on the west side, you're also thinking higher solar heat gain coefficients on that. You're not hoping to reduce those?
It's a balance between complexity of the specs and the gains that you get. Say that the same building has the same exact insulation, air sealing, all that good stuff, and the only variable is the coating that you have on the west side. Everything else, south facing, west, east facing, it's all high gains glass. And just your west facing glass is either high gains or low gains in climate zone 5. What we see from the analysis is that the best year-round performance, meaning the lowest kilowatt hour consumed for heating and cooling combined in climate zone 5 is the lowest consumption is with high gains glass on the west face, and the low gains glass on the west face produces higher energy demand because the climate zone 5 is predominantly heating dominated. Clearly, a big caveat of this is really depends on what your project looks like.
Well, I think that's the last question we have. Unless anyone else that would like to unmute and ask or make a comment before we end the session.
It looks like there's one more at the Richard Gardner.
Yeah, thank you for noticing that. That's
yeah.
kind of
Oh, I see it. Thank
falling
you.
onto the solar heat gain guidance. Anything for climate zone 2A and not creating localized overheating?
So in 2A, which is very hot and humid, we typically spec low gains glass. The one thing to keep in mind is that passive solar gains is the umbrella that encloses all energy that we get from the sun in form of heat as well as daylight. And when we block off 80% of the energy, because our low gains glass is 20%, so 0.2 solar heat gain coefficient, we also block off a lot of daylight. So you have a glass that is actually very dark. Now, within the spectrum of the low gains glass, low gains glass, you want to look at the visual transmittance VT value, specifically for the center of glass VT being greater than 60%. So 0.2 solar heat gain coefficient and 60% or higher center of glass visible transmitters. In that way, you block off a lot of the heat, but you still let a fair amount of daylight through. The risk is that you may block off all of the heat as well as you can block off most of the daylight and your window is dark. That is not what we want to do.
Yeah, and I have one more comment, I guess, or just to put it in perspective or round it down for everyone. So Enrico, I mean, since we've been discussing solar heat gain coefficients and gains, everything you said is spot on. I'm just wondering, where would you place this in terms of the priority when you're designing the building? Would you leave this for the end to do the micro adjustments on the model, or would you put this at the beginning of the whole design to try to drive?
That's a great question. It
the
comes
design?
down to which goals the project has. Because if you want to be Passive House certified, you want to have this analysis. We want to have this analysis done at the schematic design stage, because that is where you translate goals or ideas into budget items and priorities. So the schematic design is where it is best, this analysis is best done. Then as far as priorities, number one is air sealing and continuous filter ventilation. So your air seal and your ERV. Priority number two, in my opinion, goes to windows, because that drives a lot of the comfort and the condensation avoidance in your project. Then the R values or the insulation package is a lower priority that really depends on the goals of a project as well as on the budget. That is the typical breakdown of priorities that we work on projects.
Right. Thank you for that. Yeah, I think that is the last of the questions and comments we have time for. So yeah, I guess we'll see everyone tomorrow for the gradient component spotlight, and we'll see you on the next event next week.
Thank you so much for having me.